James Webb begins a voyage back to the birth of the universe. NASA is hoping for a very big Christmas present, as they plan to launch the world's biggest and most powerful space telescope on Christmas Day. Imagine a world orbiting a distant star, an Earth-sized planet that could harbor life. Proxima b, located in the Alpha Centauri star system, has captured the imagination of scientists, astronomers, and space enthusiasts alike. Could we one day visit this mysterious exoplanet? And what about the groundbreaking technologies that might make such a journey or detailed observation possible? Proxima b sounds like a dream destination, but the challenges of getting there are immense. First, let's break it down. There's the sheer distance, 4.24 light-years. Even the fastest spacecraft we've ever built would take tens of thousands of years to reach Proxima b. For context, the Voyager 1 probe, traveling at around 38,000 miles per hour, would take over 70,000 years to make the journey. And then, there's the issue of communication. A message sent to Proxima b would take over 4 years to arrive, and another 4 years for a reply to get back. This time delay makes real-time mission control impossible. Finally, we have the problem of energy. To send a spacecraft across interstellar distances, we'd need propulsion systems far more advanced than anything currently available. Could breakthroughs like solar sails or nuclear propulsion be the answer? Only time will tell. While a physical journey to Proxima b might be out of reach for now, NASA and other space agencies are developing incredible technologies to study exoplanets from afar. The James Webb Space Telescope, JWST, launched in 2021, has revolutionized our ability to observe distant worlds. With its powerful infrared instruments, it can analyze the atmospheres of exoplanets, looking for signs of water, methane, oxygen, and even potential biosignatures of life. But NASA isn't stopping there. Future missions like LUVOIR, Large Ultraviolet Optical Infrared Surveyor, aim to directly image exoplanets in stunning detail. Imagine being able to see continents, oceans, or even clouds on a planet like Proxima b. And then there's the concept of the Extreme Large Telescope, ELT, a hypothetical space observatory that could dwarf even the James Webb in size and capability. Such a telescope could unlock unprecedented insights into exoplanets, their atmospheres, and their potential to support life. The Extremely Large Telescope, ELT, currently under construction in the Atacama Desert of northern Chile, represents a significant leap forward in ground-based astronomy. With its 39-meter primary mirror, the ELT will collect more light than any other telescope, making it an invaluable tool for studying faint objects like exoplanets. Among its suite of instruments, the High Angular Resolution Monolithic Optical and Near-Infrared Integral Field Spectrograph, HARMONY, is of particular interest for exoplanet research. HARMONY is designed to capture high-resolution spectra, allowing astronomers to analyze the light from distant stars and planets in unprecedented detail. By combining high-resolution spectroscopy with adaptive optics, HARMONY can correct for atmospheric distortions, producing crisp images and detailed spectral data. This capability is essential for isolating the light of Proxima b and studying its atmosphere. Detecting biosignatures, molecules that may indicate the presence of life, such as oxygen, methane, or water vapor, requires both high sensitivity and high resolution. The light from Proxima b must first be separated from the overwhelming glare of Proxima Centauri. This is typically achieved using a coronagraph, an instrument that blocks out the light from the star to reveal the faint glow of the planet. In a study by Vore et al. 2024, researchers simulated observations of Proxima b using HARMONY's current configuration. They found that the mask was too large to isolate the light from the planet effectively. Most of the planet's light was blocked, making it impossible to gather the high-resolution data needed to detect biosignatures. This result highlights a fundamental trade-off in coronagraph design. Reducing the size of the mask could allow more light from the planet to pass through, but it also risks admitting more starlight, which could wash out the planet's signal. To address this limitation, researchers explored potential modifications to HARMONY's focal plane mask. Their simulations showed that reducing the size of the mask or offsetting it slightly could improve the instrument's ability to study Proxima b's atmosphere. These adjustments would allow more of the planet's reflected light to reach the telescope while minimizing the interference from starlight. One of the key findings was that with these modifications, Harmony could achieve a signal-to-noise ratio sufficient for atmospheric characterization in a reasonable amount of observation time. Specifically, a minimum of 20 hours of observation would be required, although 30 hours would yield more robust data. This level of sensitivity would enable the detection of key atmospheric molecules, potentially providing clues about the planet's habitability and even the presence of life. Implementing these changes to Harmony's design is technically feasible given the current stage of development. However, it would require a careful balance between optimizing the instrument for exoplanet studies and preserving its capabilities for other scientific objectives. Harmony is a versatile instrument designed to study a wide range of astronomical phenomena, from star formation to distant galaxies. Modifying the focal plane mask specifically for Proxima b could impact its performance in other areas. Moreover, the study of Proxima b is just one aspect of a broader effort to characterize potentially habitable exoplanets. Other instruments, both ground-based and space-based, will play complementary roles. For example, the James Webb Space Telescope excels in detecting infrared signatures, while upcoming missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Ariel mission will focus on exoplanet atmospheres. Together, these observatories will provide a more comprehensive picture of distant worlds. Why all this effort? Why are scientists so eager to study Proxima b and other exoplanets? The answer lies in humanity's eternal quest to answer one of the biggest questions of all time: are we alone in the universe? Proxima b is especially intriguing because it orbits a red dwarf star. Red dwarfs are the most common type of star in the universe, and many of them host planets in their habitable zones. If we can determine that life exists on a planet like Proxima b, it would have profound implications for our understanding of life in the cosmos. In the coming decades, advancements in telescope technology, artificial intelligence, and interstellar propulsion may bring us closer to unlocking the mysteries of Proxima b, whether through detailed remote observations or, one day, an ambitious interstellar probe. The search for life beyond Earth continues to drive human curiosity and scientific innovation. Perhaps, in the distant future, humanity will look back at the James Webb Space Telescope as just the first step in a journey that ultimately led us to new worlds and new discoveries. The universe is vast, and our exploration has only just begun. Please like, share, subscribe and comment. Thank you for watching my channel.